Okay, so today we're going to work with sampling distributions and sampling proportions. To start out though, I'm going to have you guys actually do a activity to kind of see how this works. This is like a candy machine, and the first thing that you're going to want to do is you can notice a couple different things in here. You can change the number of candies from the sample that you can take. You can change the machine, how many, what the probability is. In this thing, you're actually going to set it as 0.45 for the first question, and then I think you're going to leave it as 25 candies that you're going to draw, and you'll draw one sample, and you'll see, oh, there's my proportion. I found that 40% of the candies that I drew were this. And then you can keep increasing and kind of see what the pattern is, and kind of go through that and answer some of the questions. And as you can see, this, it's not exactly normal, but it's the more samples we take, the less variability, the more it will start getting towards the mean and the standard deviation not being too far off of each other. So that's the first kind of activity that we'll deal with. And after we figure that into it, we can get into the real the argument of the thing. So I've kind of tried to simplify everything in the book, and they put this kind of nice summary together for sample proportions. Your sample proportion mean should kind of make sense that, hey, your mean of your sample proportion, or your p hat, if you do this enough time, should be the same as your p, especially if it's unbiased. And then finding the standard deviation, you should remember this from your pink packet, but this is how we calculated the standard deviation in a lot of our binomial sets, and a lot of times you use proportions with binomial things. So that's would be our standard deviation. This thing right here is very, 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 very important if we want to use any kind of normal things with it. This deals with things being with or without replacement. So a lot of times, even in the candy example, when you drop the candies down here, we're not going to put the Reese's back into the machine. We took them out. So this idea is without replacement, that you can't take samples, or the samples that you draw can't be more than 10% of the population. So as you can see, my n can't be bigger, so this has to be smaller than 1/10 of the entire population. And then we have to check the normal conditions to approximate normal, again from our binomials, that the number of your sample times your proportion has to be greater than 10, and the number of samples that you take times what the opposite of your proportion has to be greater than or equal to 10. So hopefully we meet all of these categories. We're going to see a problem, and I'm going to kind of try to go through and work through a problem, and I'll try to give you a couple nice examples. Okay, so let's go through a normal problem. So it says about 75% of the young adults internet users from ages 18 to 29 watch videos online. Suppose that a sample survey tracks a simple random sample of 1,000 young adult users and calculate the proportion p hat in this sample who watch online videos. And so we're calculating this. What's the mean? Well, the mean should be 75%, unless we got some really biased survey, but the hope would be we wouldn't. So our p hat should essentially be the same as our actual population that we would know. So this is the actual, and that should be about the same. Second thing, we need to find the standard deviation of this. If you remember the standard deviation, whoops, need my pen. We want to take the square root of p times not p, whoops, over n. So for us in this case, it would be the square root of 0.75 times 0.25 over our sample, and we said our sample is 1,000. So let's pull up a calculator and see what that would give us. Oh, that went full screen. Oh, I probably should just do this first. So, pretty small number. So, yeah. So, very small number, around 0.1. So, then we should check if the 10% condition is met. We're going to assume that if you think about it, our sample has to be, like if it fails, it would have to be greater than 10 times that. So if we go, if you take 1,000 and times it by 10, that'd be 10,000. And I think there's more than 10,000 people that watch online videos. So I still think that's greater, so I'm pretty sure that meets the condition. There's probably millions of people between that age. So then the next question is this approximately normal? Well, to check if it's approximately normal, we have to do n times p and see if that is greater than 10, and then do n times not p and see if that's greater than or equal to 10. So our n for this case is 1,000. That's 0.75. So yep, 750 is bigger. So again, same thing for this, 1,000 times 0.25, and that's 250. And that's definitely bigger than 10. So we're good in both these cases. Now their last question is, hey, what if we change the sample size? So instead of using something rather than 1,000, we use 9,000. So again, the first thing we want to check is, does the 10% rule still apply? Well, I'm pretty sure that there are more than 90,000 people that watch this, so we're good. Like that, our population is definitely bigger than that 10%, so we're good there. The next thing is we got to think about what would change. Well, I mean, our mean hopefully would stay the same. Like taking more type things shouldn't like change our mean. So the only thing that probably would change is our standard deviation. Oh, also we should check the normality, but if it worked for a smaller sample size, of course it would work for a bigger sample size. So let's see how it would affect our standard deviation. So our standard deviation would be calculated exactly the same way. But that means that this, instead of being 1,000, is 9,000. So it changes it by a factor of 3. We can see what that really looks like. So yeah, so 0.004 now. So it just makes the variability smaller by taking a bigger sample size, which makes sense because the bigger the sample size, we should keep reducing the variability. Try the different problems today. They all pretty much follow this same archetype. Again, your p hat should be the same as your p. Your standard deviation is calculated by that formula. The condition, you want to make sure your actual population is more than 10% of the sample, or without replacement, then you run into some issues. You want to make sure that like normality is checked, so take n times p and see if that's bigger than 10, and n times 1 minus p and see if that's greater than 10. And then the last thing generally they have you do is they ask you something about like, what if I took a bigger sample size? Well, if you took a bigger sample size, it should decrease your standard deviation and reduce your variability, but it will not change where your mean is. So if you have a biased sample, it will stay biased.